And with our block diagram completed. This is the third video in the series in which I have set out to build my own high-end router, and with our block diagram complete, we can now move on to the bill of materials, which is just a fancy word for saying let's pick all the parts that this device is going to be made of and put them in a list. Before we start, I have to first satisfy any experienced embedded developers that might stumble upon this video and go, what the hell is this guy doing? To which my answer is yes, I know it's sloppy and not very accurate, but it's good enough. Good enough to calculate our margins in the next video in this series. Good enough to make a financial plan after that. And finally, good enough that any less experienced subscribers of this channel will have gotten plenty of value out of it. If, and I know it's a big if, I succeed with this project actually becoming a reality, what we will do with this bill of materials is two things. A, when we start with the actual development, we're going to share it with our chosen hardware developer and use it as a starting point of our conversation. And B, we're going to compare it with their suggestion, or better yet, the actual bill of materials that will get used for when this device goes into production. If nothing else, to see how much we were off. I'm going to make a wild guess and say less than 20%. But before we begin, let's answer the one question most people ask me when I show them this project. Where do you even start? And actually, it's not as hard as it might first seem. Here's how I started. Not saying it's the right way or the wrong way, it's my way. I first looked at my competitors and analyzed as much of their networking devices as possible. At this stage, I was mostly concerned with the type and performance of the CPU they are using, along with how much RAM. The latter most often isn't an issue from a performance standpoint, but it has a relatively big impact on the final price. For example, 8 GB of RAM costs, let's say, 30 to 40 euros. So if we'd put 16 GB on our router, which would only ever need 8, that would make it at least about $100 or euros more expensive, margin included. This is an example, of course, as we have yet to calculate our margins, but I hope you see the point. We have to be mindful of the price of each component and make sure it will be properly utilized. Otherwise, the device will be needlessly overpowered and consequently more expensive. Why focus on the CPU first? Well, because it's usually the most expensive chip on the device and because all other choices often heavily depend on it. We ruled out x86 architecture pretty early because not only it is much more complex to develop custom hardware with, raising the final price, but the CPUs themselves are also much more expensive, often twice the price of their similarly capable ARM counterparts. Once we made the decision to go with an ARMed architecture, the search for the optimal CPU narrowed significantly, as the other two very important requirements for me were having at least two 10 gigabit Ethernet ports and running a 64-bit instruction set. If you literally enter the 64-bit ARM CPU with 10 GB networking into Google and click the first couple non-sponsored results, you'll see one manufacturer that keeps popping up: NXP. And that's exactly how I started before I got in touch with the actual experts that are now helping me with the development of the device. I looked through NXP's website until I found the best candidate, Core IQ LS1046A. Then I got in touch with a couple of my friends that work with embedded devices and asked them what they think. About the CPU, that is, because they all thought I was crazy for trying to develop my own router. Nevertheless, turns out my choice was spot on. The CPU in question not only has the optimal performance for a device I envisioned, but also comes with a couple of features that I initially weren't even on my requirements list. A, it has something called packet processing acceleration, which is just a fancy word for saying that packets are processed by a separate hardware that takes that load away from the CPU cores. B, it has an integrated security engine, which again offloads protocol processing such as IPsec and SSL from the main CPU. And C, is therefore very efficient, running at max 12 to 15 watts when at full load, which means we can easily cool it passively, bringing the overall cost down as we don't need any fans. Plus, it will be silent to boot. One thing you might not know is that in chip production, manufacturers often sell what are called development kits or development boards. These contain the chip in question, surrounded by any number of other chips and connectors to showcase either a particular feature or all of them. The LS1046A that we are using, for example, has 2 development boards you can get. But only one of them supports 10 gigabit connectivity, so the other one is out of the question for our needs. But the board itself isn't even the best part. It's the documentation that it comes with. In fact, you don't even need to buy the board, you can just register an account on nxp.com and you'll be able to access it all completely free. The spec sheet, schematics, and even a complete bill of materials. But wait, you might say, why are we building a bill of materials if the manufacturer already provides it? Good question, dear subscriber. You are a subscriber, right? The bill of materials that comes with the development board is very useful to us, as you will shortly see, but it cannot replace the one we're currently making, primarily because of 2 reasons. A. Reference design boards usually contain absolutely everything that a CPU that's on it has to offer, and B, some components on it might be obsolete or are nearing what is known as end of life, meaning manufacturer will soon stop producing it. The latter is especially important because you want to be able to offer support for a particular device for at least 10 years, if not more. And you cannot do that if a particular part is no longer being manufactured. Now, with the theory done, let's start building our own bill of materials. And for that, we will use Google Sheets, which I'll open to everyone and link to in the description so you're able to check it out for yourself. Let's go. The first thing we'll pick, the CPU. Let's navigate to the NXP website where the CPU is listed and see what kind of options we get. As you can see in this table, there are about 30 variants of the one we have picked. The 2 most distinct features being the number of cores and max CPU frequency. Let's go with 4 cores and 1.6 GHz. As you can see, we're now left with 4 choices, and if we check their differences, you can see the 2 of them are rated to run at minus 40 degrees centigrade. This temperature range is usually referred to as industrial as opposed to consumer grade, which start as 0 degrees centigrade. The difference between the 2, apart from the lowest operating temperature, is obviously the price. Industrial being more expensive, of course, which leaves us with the 2 top ones, the only difference being the security engine. Without going too much into it, let's choose the one that includes it, because the difference in the final price of the 2 is less than $1. Now that we have our very first part, let's put it into our spreadsheet. Actually, let's first organize it a little bit and make a couple of columns that will make our life just a little bit easier. Let's use the first column for how many units of the same part we will need, which in the case of our CPU is 1. Then our second column will be the manufacturer and our third the part number. In our case NXP and the LS1046A. The fourth column will be the price per 1000 units or one we find that's closest to that. So for our CPU the price is just about $73, so let's put that in. Note how the website says that's the price at 100 units. This only means that at 1000 units it will be even lower. Onwards to the next column, and here we will use some spreadsheet math. For the CPU it isn't relevant, but some parts such as RAM we will need more than 1 on our PCB, so what we need to do here is simply multiply the first and the fourth column, which you do like this. You click into this FX field and enter equal sign, then you click the first field followed by entering the asterisk, which is the symbol for multiplication, and finally the price field. To test whether it's working, try entering 2 into our quantity field and you should see the final price double. Now let's add our final column and call it remarks. We won't fill it here, but I find it useful when, for example, I find the price of a part, but then the distributor gets in touch and says they're preparing a better one for me, so I just put in something like waiting for distributor. Now that our first part is in, let's also make it look a little nicer and make the header cell stand out a bit by making the background dark gray and the text white and bold. And before we continue, let's also make two special cells, one of which will be immediately useful and the other we will touch on in one of the future videos. The first one will be total parts cost, which is exactly what it sounds like. The cost of all parts for one unit of whatever we're making. Again, similarly to our previous calculation, we will enter equals in the fx field, but we will now follow it with the word sum, all caps, followed by an open parenthesis. Then simply click and drag from cell F2 to say F50. It's not super important because we can always go back and stretch or shrink the range. Now just enter close parentheses, hit enter, and we're done. Again, to test, enter an arbitrary number into cell F3 and see the total part cost change. Second number in this special area is not the one we're gonna calculate. Instead, we're simply going to write it down. And we're gonna call it asking price, or the price we aim to sell our final product for. Let's say for our example we'll go with $5.99. Let's format these two for currency and we're all set to proceed with our second part. If you watched the previous video in this series in which we built a block diagram, then you already know the next parts we will add are going to be power related. And for that, we'll look into the datasheet of the reference board and reuse exactly the same ones. No need to reinvent the wheel. If we scroll to page 14, you will see the block diagram of power delivery for the reference design board, and what we'll do is just basically take all the parts it has and simply enter them into our spreadsheet. And if you don't know who the manufacturer of a particular part is, no worries. Just literally paste it into Google and the first non-sponsored result will most likely be accurate. In our case, for the LTC3866, it's Analog Devices. But you don't even need to visit their website. Instead, let's open either mouser.com or digikey.com to get the price of the part. Just find where it says quantity 1000 and copy paste it into our sheet. Now let me show you a trick. If you click on the lower right corner of the F2 cell where our final price is and drag it down, it'll copy the same equation to all the rows beneath it. And not only that, it'll automatically calculate final prices for each part as well as the total parts cost. Magic, baby! I'll speed up the footage for the rest of these parts because there's no need for you to be watching me copy pasting stuff back and forth now that you know the process. Except for this part. Because as you can see here, it says it's being discontinued. What we will do for now is put it into our spreadsheet anyway, but we will put a remark that we need to find a replacement. Onwards to clocks. Exactly the same procedure as with the power delivery section, the only difference being we literally just need to put 3 parts in. One clock generator, a real-time clock and 2 buffers as per the block diagram in the reference datasheet. The real-time clock is not that well documented as it's only listed in this I2C block diagram. But let's put something else in here as it's also only clock related, a coin battery and its holder. You've probably noticed how every PC motherboard comes with these 2 parts and it's exactly the same reason, so it doesn't lose the track of time. If we didn't include it, we'd have to set the time and date every single time the device would be turned on, which wouldn't be very convenient to say the least. Unfortunately, this datasheet doesn't list these 2 parts, although they are on the board if you look at the pictures of it, so we have to look for them on our own. But it's not a big issue because we'll use CR2032, one of the most common coin battery sizes in the industry. And consequently, there's plenty of battery holders for it, be it mounted horizontally or vertically. RAM next. And here we have to make a choice. We can either put a socket on our PCB and let the user buy and stick their own modules, or we can embed the RAM chips ourselves directly on the PCB. Let's look at the pros and cons of each approach. With a slot, you're obviously much more free when it comes to both capacity and the choice of manufacturer. By the way, did you know there are just 3 first-party manufacturers of RAM in the world? Micron, SK Hynix and Samsung. And we'll use Micron. When it comes to adding a 288-pin slot for memory, The downside is that you have no control over what users will put in, meaning there's no realistic way of testing all possible combinations, which will likely mean you'll have to deal with additional support. Plus, there's no guarantee that even the parts that you do test with your boards will even be in production for 10 years or however long you want to manufacture and sell the device. But on the flip side, if you decide to put memory chips directly on the PCB, then you lose the option to upgrade to bigger capacities down the line, but you know for a fact that the RAM that is on your boards is well tested, working, and is guaranteed by the manufacturer it will be produced at least until X years into the future. There is no right or wrong here, it comes down to what the market that you'll be building the device for prioritizes. We'll use embedded RAM as it's highly unlikely people will need more than 8 gigs in a router, even one with 10 gigabit ports. While we're talking about memory, let's also go over the storage chips, as they'll come from the same manufacturer and are actually very similar to one another from a hardware perspective. We have exactly the same choice as with RAM here. We can either add an M2 slot on the PCB and let users plug in whatever they want, or go with an embedded solution. Exactly the same pros and cons as well, which is why I decided to go with a 64GB eMMC drive. Before we move on to storage, we also have to add one final part as seen in this block diagram. It says QSPI memory, but as I explained in our block diagram video, this is also known as NOR flash and is used to store boot code for the device. If you follow that video, then this next section is very important, as we will turn our general purpose embedded device into a router. Yes, we need to add PHY chips. For 10 gig one, the spec sheet uses the one that's pretty much the golden standard, and that's a chip called AQR113C by a company called Marvell. And it's actually exactly the same one that's used in the Mac Studio that I'm editing this video on. So if it's good enough for Apple, then it's also good enough for me. And for the 1 gig PHY, although the reference design board uses Realtek chips, we're also going to look into Marvell's catalog and choose our alternatives from there. And since we have a limited space on the PCB, we'll choose a quad PHY chip, meaning it supports up to 4 ports on a single chip. Here's a problem with these two chips though. As you can see, there are none listed neither on DigiKey nor Mouser, so the prices were a bit trickier to get. So what I'll just do is I'll put them into our spreadsheet, the ones that I've gotten from a distributor I spoke with on the phone, and keep in mind these are approximates, but they're close enough. But we're not done yet with the networking part, because in order for our board to have SFP plus connection, we also need the cage, a connector, yes, these are two separate parts, and a chip called a retimer. All of them are listed in the spec sheet, so let's just go ahead and find their prices and put them into our spreadsheet. All that's missing now are the RJ45 jacks, and since the spec sheet doesn't list their part numbers, we're basically free to browse around Mouser or DigiKey while being very careful to pick the ones that include magnetics. I've explained what they do in the previous video, so I'll leave the link up here and in the description below if you want to check it out. For now, just keep in mind that if we choose an RJ45 jack without magnetics, then we need to add them as a separate chip. Here I'm gonna cheat a bit and just use 5 of the same RJ45 jacks for both our 1 gig ports and 10 gig ports, although the 10 gig ports are usually a couple of dollars more expensive. We're more or less done with the networking chips, but while we're here, let's also add all the other connectors that we'll also need. First, the obvious ones. Since we're gonna use USB-C for power, console and host connectors, I went ahead and found a vertical one that should look nicely on our board. There is no hard and fast rules here. Browse around and read through a couple of datasheets and pick the one that you like and fits the board you're designing the most. Now the not so obvious ones. We'll also need a JTAG connector for debugging and a Molex connector for the mini PCIe slot. I'm sure I have missed some, but these connectors are a dime a dozen, so we'll address them in a different way shortly. Almost done. We have all the major chips in place. But a device costs much more to manufacture than the sum of its chips. We haven't added any passive components, screws, feet, the cost of anodization, or even the PCB assembly service itself. So let's create a section named Other and first put in the estimate price of what we at Incubator call chicken food. If you check the reference design board schematics that it comes with, you'll see it's littered with tiny capacitors and resistors, all of which cost cents individually, but add up to about $30 for a board of this size. If you want a more accurate number, here's where the included bill of materials come handy. Feel free to investigate and copy over each capacitor and resistor manually, but for our needs, we'll just put in $30 and say it's good enough. We'll also approximate the cost of PCB manufacturing itself, you know, taking raw sheets, plotting the solder mask, etching the copper away, applying solder, and finally picking and placing our components. If you're curious how all this works, let me know in the comments below, and I can also give you a tour of the facility that does that before the router we're building is ready. But for now, let's estimate this process to cost around $30 per board as well. And now for the big star of the show, the aluminum case. Since we shrunk down initially planned size, the price of the raw aluminum came down as well, quite significantly actually, from around $40 to only $13. Yep, you heard that right. Now we also need to add $70 for CNC machining time, $40 for anodization, and around $10 for feet, screws, and aluminum heatsink combined. I know I'm rushing things a bit, so if you'd like more clarification on any of these numbers, please let me know in the comments below. Before we wrap this up, if you watch this far, you're an absolute legend. Thank you. I have a small request to make though. After you're done watching this video, please click the first link in the description. It's a short survey I'm conducting on how much people would be willing to pay for a high-end device like this. It'll only take you 2 minutes, I promise, but it will make a world of difference to me. Plus, I will make another video as to why I'm asking the questions I'm asking, and I get my answers and you get more content. Win-win. Now let's wrap it up. As you can see, the final price for our router gets calculated to $539. And that's only if we manufacture at least 1,000 of them. If we decided to only ever make, say, 100, you saw for yourself that the prices for each component would be significantly higher, sometimes even double. And this also means we have set the asking price for each unit way too low, as this is not nearly enough to make it into a sustainable business. But more on that soon, so make sure you're subscribed. See ya!